And now it's time for our guest, Kevin Gill. Kevin, welcome to the Weekly Space Hangout.
Hi, Fraser. Thanks for having me.
Man, I can't believe that we haven't had you on the Weekly Space Hangout so far. So I'm really glad that we're able to get you here. For people who have no idea who you are, can you give your introduction?
Yeah, I'm currently a software engineer at NASA JPL, working with sea level change tools, with the orbit viewer component for the Center for Near Earth Asteroids, and a methane tool for Southern California.
So, which is it, like one specific spacecraft or?
Now, currently those are tools that aren't necessarily tied with any spacecraft, except for some of the work I do is with imagery with Cassini, but we don't have that one anymore.
Yeah.
So that's mostly just outreach imagery processing.
Yeah. And you and I've been friends for many years. We had kind of connected before, sort of on the interwebs, and I sort of drafted you into helping us out with some of the videos that we were doing for the Guide to Space, and that just like somehow turned into your actual whole career.
Kind of did.
Yeah. Yeah, but I mean, I think one of the things that you're really well known for out on the internet is that you have also been doing a lot of really great work on this data that's coming back from Juno and the Mars Reconnaissance Orbiter. And this is almost like in addition to your regular day job, right?
Yes.
So, yeah, so tell us about sort of about how you kind of got into this part of it.
I don't know exactly because originally I was doing all the computer graphics because I had written that tool that rendered that Mars back in the day, and then I was doing stuff in Blender and then Maya for the Guide to Space, helping you out. And then I just thought, well, there's actual cameras out there.
Yeah.
So I think I started originally with a high-rise context image of the Cydonia region on Mars. I think that was the first one I did, and then I found
And what did you
Cassini.
what did you use as your data source for that?
Oh, that was out of I think those were in PDS, the original data source. So I had to find all the tools and all the stuff to convert those from their image
That's
formats
the
over.
planetary data system for those of you keeping score at home.
Yeah,
Yeah,
yeah, yeah. Yeah, you can't go too deep into the acronyms.
yeah. So,
Um,
uh,
yeah, no, and in fact, you had, and I apologize for everybody, who's listening to this as a podcast. You had done these great simulations of what Mars would look like terraformed, and you'd sort of shown oceans and what would be the green planet and the blue planet versions of Mars. And I know a lot of times when you see a picture now of a terraformed Mars, that's Kevin's picture that you're often seeing, and it's sort of made its way even into a certain company down in Hawthorne, I believe.
yeah.
But you can't see too much more about that. So, but right, and so then you started to like do larger and larger simulations of Mars, and so you're taking actual data of Mars that's captured by various spacecraft, and then what are you doing with it?
Okay, so with those ones, the high rise folks at the University of Arizona, they're taking that high resolution imagery from the high rise camera on the Mars Reconnaissance Orbiter, and they're using a method to derive a digital elevation model. So it's 3D data. So I'm taking that into a rendering or graphics program called Maya, and then I just kind of render it as if you were there. I place the camera down on the surface. I overlay that the actual imagery over that, so you can see the rocks and the different color variations. Though a lot of the color is subjective, I kind of make it up based on what you see with a much thinner RGB band, uh, just because there's not usually enough color for me to work with. So I just use different lighting techniques in Maya.
And I'm posting a picture for the folks who are watching this live, and we've got this really cool image of the surface of Mars, but it sort of looks as if you were standing right on Mars, looking at standing, say, at the edge of a crater, or another image of Schiaparelli, and again, it's just an astonishing image. It looks like the kind of picture that you would see if you were orbiting really, really close to Mars, closer than I guess anything that's, that's there right now. And so this is just like 3D data gathered by the spacecraft, and then you are rendering it into something that's more artsy.
Yes, artsy is yeah, because I'm not attacking those at a scientific level.
Yeah. Yeah, you're washing out all the scientific usefulness out of the image.
Yeah, and just trying to get more of the artsy or inspirational type view.
So can you talk a bit about the Juno Cam?
So the Juno Cam, I'm sure most people are familiar with that. That's the camera they almost didn't include on Juno, and thank God they did.
Who thought it was, that they wouldn't need a visual camera on a spacecraft going to Jupiter?
I don't know, but if I was dictator, everything in space would have a camera.
Yeah.
But yeah, so they've got that camera. It's about the quality of a webcam or a dashboard cam, so it's nothing too fancy. So they take that. They're taking the images.
Just be careful with that microphone. It's scraping again, so just be a little careful with it. Yeah.
Okay. So yeah, they're taking those images as the Juno comes in for the perijove, as it makes this close encounter, and transmits that back to us. So I've written a number of scripts that goes and takes that raw image data, spits it out in color for me, and then some Photoshop and Lightroom later, we've got an image.
And I mean, this, with the whole Juno Cam, I mean, there was a real specific relationship that they were trying to build between the researchers and the spacecraft and the general public. And so this is, I mean, what you're doing is exactly what they were hoping that people would do.
Absolutely. And it's been a big success for them, as far as I can tell. We've got a number of really good image processors on that data, sharing it out. And I think it's been a big win for them.
Now, when you talk about good image processors, you're talking about human beings like you who take these images and produce an artistic interpretation of what you're seeing. Did I lose him?
Right. So either people that are taking the color data down or the little more higher resolution raw data, either myself or Sean Dorn or Gerald.
And has some of this material kind of come back in and been used for science at all?
It has. Not any of mine specifically, but some of it they've been able to use. You've seen the animation of the Great Red Spot. They're able to derive some three-dimensional data from images that are taken over a similar area, and that was where they were able to come up with the North Pole cyclones, that three-dimensional image.
Yeah, I mean, I think it's safe to say that these images that we're seeing from Juno are the most spectacular images of Jupiter that have ever been taken. Like, the level of detail on the cloud tops, on the swirling clouds, even some of the structures, you can see the sort of three-dimensional shape of some of these cloud tops is just astonishing. And again, wow, can you imagine if it was a better camera as opposed to a dash cam? And the fact that you guys have been able to pull these images out to that level of quality is just amazing. So let's say that a person is listening to this or watching it and really wants to get involved in processing some of these images. How can they do this?
It's pretty easy. You just go over to the Juno Cam mission website, and they've got a whole portal set up for image processing. You're able to download the raw data, either two levels. One, they've already map projected with some of the color. The other one is kind of just even more raw, which is pretty much in the grayscale strips as the camera sensors see it. And just it's easy to go pull those right into Photoshop and make your adjustments.
So you would pull them in and then set them as different colors and mess around with the balance between the images and pull out. So where are some places where maybe there's a lot of this kind of planetary data, image data, that citizens could go and get their hands on, but maybe they just don't realize it?
It's almost all of it's there on the planetary data system, that PDS that I mentioned. So they've got the full mission records for Cassini, for Voyager, Galileo, a lot of the Mars missions, just about anything else that's up there. And that's all the calibrated data records.
I was actually just seeing an article today from Emily Lakdawala, who was our guest last week. She dug up all of the images that had ever been taken of Deimos, the Martian moon, by the Viking 2 orbiter, and built a really nice, fairly, took all of those images and brought them together to make one composite image of Deimos, which is pretty amazing.
Yeah, that's a really complex thing to do.
Yeah. And then the other one I think, which is great, is like a lot of people do work with the Hubble Space Telescope. Have you played around with any of that data at all?
I have. I did that about a month ago, maybe a little bit more. I was able to pull down some Hubble data. I just did a little bit of it. I think about 10 or 15 images from Hubble. And I was kind of addressing it mostly with the same kind of thought process I do with planetary data, which isn't 100% accurate way to address it, but I made some pretty pictures.
Yeah. I mean, it's always so funny to me, right? When people say, "Oh, NASA is holding back all of this information. They're, they're doctoring all this data. They're not releasing, because NASA doesn't release this information to the public." But NASA's just got this fire hose of data that is constantly just pouring out way too much material that they can even ever use. I forget what Reconnaissance Orbiter has sent back hundreds of thousands of images. Cassini sent back hundreds of thousands of images. Like, there's just no shortage of material to look at.
Yeah, there's terabytes of it. There's a lot.
So, I mean, I can see, and I highly recommend, the best way to look at Kevin's stuff is to go to his Flickr page. I'm not sure why he still uses Flickr, but that's where you can find it. And go to check it out. And he's got a lot of just, images of Jupiter, these images of Mars I was mentioning. If you go even further back, you can see stuff like what Earth would look like with rings if it was in Los Angeles, things like that. What challenges are you working on now? What's your next big plan?
Right now, I actually just wrote a new pipeline for Juno Cam. So they released a new Juno processing tool for the USGS ISIS-3 processing software. So I extended that into a new pipeline that's working with the calibrated data records that I'm pulling off of the PDS. And I've pushed that up on GitHub, so that's all open source, along with all my Cassini and Voyager processing stuff. So it's pretty much getting that accurate and then start working with that and seeing what else I can do.
So what will that let you be able to do?
I can do reprojections with it, better color calibration, and better alignment of the data. Because that's one thing I haven't really been able to do up until now with Juno Cam and stuff, is get the alignment right between those color strips, and now I can.
Right. And so to, like, when you've got those different images and the different wavelengths, to be able to put them all together into one composite image, is that? Yeah.
Yes.
Yeah.
Yep.
Yeah. For me, even though I use Photoshop almost every day, it is just a incomprehensible piece of software. I just sort of press buttons at randomly until the outcome that I'm hoping for happens. And
I'm still figuring it out.
Yeah, and it's a different way. Like yesterday I was Googling just like, how do you draw a box in Photoshop? And it took me, 10 minutes to be like, oh, okay, this is how I draw a box. Or how to crop on a layer. Anyway, yeah, it's very complicated. Well, Kevin, what's the best way? I mentioned your Flickr page. What's the best way for people to follow more and see what you're doing?
Best way is on Twitter at Kevin M. Gill. Another way is on Instagram.
Nice.
It's at Apoapsis with a Y between those two S's at the end. Kind of an intentional misspelling.
Yep. Awesome.
So those are my the two primary places where I post everything. All the pictures go up in Flickr as opposed to the other two.
Yeah. Well, Kevin, thank you so much for joining us on the Weekly Space Hangout. I highly recommend anyone who wants go and check out his photo stream. Just amazing imagery, and get inspired. If you have any interest in sort of playing around with some of this data on your own, by all means do it. I think you'll find it fairly accessible, and Kevin and a lot of these other citizen scientists have provided tutorials and a lot of ways for you to kind of see the ropes and move away from just those same Hubble imagery that we've seen a lot before. Make some new ones out of that raw data. It's all there. So thanks, Kevin.
All right. Thank you.
All right.
All right. Bye-bye.
All right. Now it's time to get into this week's show. All right. Move this in a better location. Okay. Welcome to the Weekly Space Hangout for Wednesday, April 18th, 2018. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about TESS launched. Yes! The Russia's going to exit the commercial launch market. Diamonds, evidence of long-lost planets. Let's change all the unit systems again. And look at these baby planetary systems. Joining me this week, we've got Dr. Kimberly Cartier. Kimberly.
Hey, Fraser. Happy podcast day, everyone, and happy TESS launch day.
Kimberly is Earth and Space Science reporter for EOS Magazine. We've also got Dr. Paul Matt Sutter, back after last week's absence. Hey,
sorry.
He's an astrophysicist at Ohio State and the host of Ask a Spaceman.
Always good to be back.
What is the OMG particle? No, we don't have time for this.
Gotta wait.
For the podcast listeners, Paul's got a strange thing on his blackboard here. Who knows what this particle is?
With words.
And you're going to have to check out his podcast to find out what it is. And we've also got Dr. Morgan Renberg, the Director of Scientific Presentation at the Fort Worth Museum of Science and History, and Dinosaur Guard.
Yeah, that's right. Hey, Fraser, I'm tearing myself away from the world of dinosaurs for 1 hour, to talk about TESS and all the awesome space stuff.
For people who missed it before the show, we were just nerding out about dinosaurs for like 10 minutes. We nerded out for about 15 minutes before we started the show, and then we kept nerding out about it for another 5 minutes after we started the show. So we love dinosaurs as much as we love space. But
we also learned that I don't know anything about dinosaurs.
Except for Kimberly, yeah.
No, not me.
The problem is that we don't get access to all these great images. With NASA, all the images are in the public domain, while dinosaurs, each one is an artist.
Where are my satellite images of dinosaurs?
Yeah, exactly.
A conspiracy in action.
Yeah. The aliens who are like 65 million light years away, they have the pictures of our dinosaurs.
And that's what makes producing a general science show for something like YouTube so much harder than something like a space show.
If you're a dinosaur expert out there, please make content.
Yeah.
Make content. We desperately need it.
Right. So you're like, you need an image of a dinosaur, and you just have to use take pictures of little dinosaur models that you found.
All the images of dinosaurs on Wikipedia are photos taken of museums with like random people in the background, and they're all terrible.
All right, well, before we get into this week's stories, I just want to remind everyone a big thank you to the WSH crew, the Weekly Space Hangout crew. These are, of course, our producers, our partners. You can join this fabulous community. Go to wshcrew.space. The other thing I want to remind you is that this is a podcast as well. And if you want to support the show, one of the best ways that you can do that is to give us a rating on whatever podcast machine you're using, be it iTunes, Google Play, I don't know, Stitcher, Anchor, wherever it is. Flickr.
That's not right.
Yeah, it means a ton.
I don't know much about podcasts, but that's not right.
It means a ton to us, and it helps more people find out about the show. So if you want us to be able to keep making shows, we need your support. Tell the world about our show. That would be great. Thank you so much. All right, let's move on to this week's news, and I want to talk to Kimberly.
Yes.
About the test launch.
Test
launch, yes!
It happened. Tess, it launched the Transiting Exoplanet Survey Satellite, which is the next Kepler, but bigger and better and more planet.
Super Kepler.
Stuff. It launched today, not more than an hour and a half ago, as of the time we recorded this on Wednesday evening. So TESS is the Transiting Exoplanet Survey Satellite. It's a transit finding mission looking for transiting exoplanets, just like Kepler did, built by NASA and MIT, and it launched this evening aboard a Falcon 9 rocket. And I've never been so happy that Falcon 9 launches are completely ordinary and go off without a hitch, because it was perfect. I mean, I will say there was a 2-day delay. They had some issues. They were supposed to launch Monday evening. They about 2 hours before the launch, they scrubbed it in order to do some more guidance testing, but they rescheduled for today, and everything went off perfectly on time, and all of the different stages of the rocket launch went fine. The TESS telescope decoupled just fine, and it's on its way to its very, very elliptical and very new orbit, which through my research, I learned that the satellite itself is going into an orbit that no other satellite has ever tried before. But it could be very, very interesting. So
why is it using that orbit?
Yeah. What is the orbit and why are they using it?
Okay. So the orbit it's a highly elliptical orbit that's in a 2-to-1 resonance with the moon, which means that it makes 2 orbits around the Earth for every orbit that the moon does. And by doing so, it uses the combined gravity of the Earth and the moon to keep it in a stable orbit without having to expend any fuel whatsoever once it gets into orbit. They don't need fuel.
Yep.
They can
they don't need to do station keeping.
It goes around the Earth in 2.5 weeks, points its antenna to Earth and sends all its data down, and then keeps on going. And by doing so, it can stay in this orbit stable for decades without ever needing to refuel. So the TESS mission nominally has a 2-year primary mission, and in that 2-year primary mission, it will observe and scan the sky for planets 85% of the sky. It is an all-sky transit mission, which is very different from Kepler, which stared at a very tiny patch of the sky for 4 years.
Stamp.
Yeah, it's like this tiny little piece of the Cygnus constellation that Kepler looked at. TESS's field of view is incredibly large. It's 24 by 96 degrees in one swath, which is bigger than the entirety of the constellation of Orion.
Wow. And it's not giving up, it's not trading that large scanning area for less precision or depth compared to Kepler?
So depth, it necessarily, because it's an all-sky mission and has to scan the entire sky in 2 years, it won't go quite as deep as Kepler did. For each of that,
that's like a feature, not a bug, right?
That is a feature. It's a feature in a different way than Kepler was a feature.
It's a feature.
I wouldn't say one is better than the other, but for 27 days at a time, TESS will stare at one 24 by 96 degree patch of the sky. It will stare at it for 27 days, send its data down to Earth, and then it will move on to the next patch. And it'll systematically go around the southern sky and then flip and do the same thing for the northern sky. And it'll get about 85% of the entirety of the sky. But because it only spends about 27 days on a particular patch, it can only really do about 200,000 of the brightest stars in the sky. And because of that, most of the targets that are looking at are about 10 times closer than any of the stars that Kepler looked at. So not quite as deep of a survey, but it'll have many more targets over the entire sky.
So what is the fact that it's constantly moving like this? What does that do to the periods of planets that can find? You know, Kepler was staring for years at the same patch of sky, but what if all these transits are happening at times when TESS isn't looking?
Sure. So for planets in the parts of the sky where it only looks for 27 days, the planets will have to orbit 2 or 3 times within those 27 days. So they're going to necessarily be short period planets. Now, if you're around an M dwarf, those short period planets might still be in the habitable zone. They might still be small and rocky. But if you're looking around any of the sun-like stars, they're not going to be habitable at all. But with Tess's search pattern, there's a circle at the southern celestial pole and the northern celestial pole that will have continuous coverage for an entire year. So in those parts of the sky, there may be some longer period planets that Tess will be able to observe.
But I mean, as you said, like, this is going to be able to last for a very long time. So we may see it's maybe not after the first 2 years, but maybe after the next 2 years, and after the next 2 years, and the next 2 years, it's going to keep building up this data and start to provide planetary candidates that could very well be these Earth 2.0s.
Yeah, and certainly given the fact that all the targets that it's going to be looking at, all the stars are going to be much closer. Any of the planets that they find are going to be much closer. They're going to be much better targets for follow-up missions, either from the ground or from space.
And correct me if I'm wrong, could it find an Earth 2.0, or is it not sensitive enough for something that small?
I believe if it could detect a transit of an Earth 2.0, but it wouldn't be able to verify it in its primary mission lifetime. Because to verify a transiting planet, you need to observe that transit at least 2, hopefully 3 times in order to know that it's the same planet that you're seeing, and in order to build up that signal to noise ratio. Because an Earth-sized planet around a sun-like star, that's a very, very tiny signal. So you need multiple transits for that. And in 2 years, that's not quite enough time. But if there was an extended mission lifetime, or if it was followed up with other telescopes, maybe Tess finds 1 transit and then another telescope follows it up with 2 or 3 more, sure.
And I think that's the key, right? And Larry Beckham mentioned this in the chat, that Tess is James Webb's finder scope.
Yeah.
Right.
So I think we've talked so much about how James Webb will do great things for planets. It's not a planet finder. It's the zoom lens for the planets, and this is the wide angle lens that will see all the planets and serve as give the bank of planet targets for James Webb to go look at.
So when you think of that
motivate? Oh, go ahead, Fraser.
Oh, I was going to say, when you think of the math, right? It's going to have. It may have only a chance of capturing a possible transit in that region that it's going to be observing, but then it's going to be dumping all that data, and other ground-based telescopes are going to be doing much more regular surveys, watching these candidates and confirming them and filling in all the gaps. So so Tess is just
atmospheres.
So Tess is just this dragnet that is just gathering as much potential candidates as possible, and then just dumping them at the feet of the astronomical community, and they're going to be following up with every instrument at their disposal, whatever's appropriate, to confirm these worlds.
All right, so there's 2 more points about Tess that are like 2 of my favorite points about Tess that I haven't mentioned yet. The one is that the so-called sweet spot for Tess will be finding small planets around M dwarf stars, and that's something we talked about just last week with Proxima b, where it may not be such a good idea to have a rocky planet in the habitable zone around an M dwarf star. Maybe not the best prospect for life, but again, there are so many unknowns about that just trawling in those M dwarf planets to see what sort of variety and what sort of possibilities are there, what different variations there could be on this common theme of red dwarf planets. That's something that Tess is going to be amazing at doing. And the second thing is the all-sky component of Tess. Will give us a decent idea of the distribution of planets in the Milky Way, which regions of the galaxy are better for planets. It's sort of, galactic habitable zone idea that people keep throwing out.
Are there reasons to think that that distribution shouldn't be pretty uniform in all directions close to the sun?
Well, we don't know. That's the issue. In different parts of the galaxy, the stars have different metallicity. They have different ingredients that they're building things out of. And most of the planets that we know of are in that one patch of the sky that Kepler looked at, where there are a lot of stars, and it's pretty close to the center of the disk of the Milky Way, which we know is great at building things. But what is it like elsewhere?
I think it's also really important to note that this is an Explorer class mission. The whole price, including launch on the Falcon, was $200 million.
Yeah, it's tiny.
Kepler was twice that. So
it's tiny.
Yeah.
But I mean, it was built in what, 5 or 6 years. That's how long I was in grad school. Yay. And I mean, it only has a 2-year primary mission. Now, who knows what it'll do after that, what the funding situation will be, and whether it'll continue to be operating. I mean, the telescope will be fine.
I checked.
Have any reaction wheels?
It's got 4 reaction wheels.
No.
Yeah. It's only got 4. Let's just count
Survey
them
telescopes.
down. 4 reaction
Survey
wheels.
telescopes like this are really inexpensive to operate too, because you don't necessarily need a whole science team kind of picking and choosing what to look at. You just kind of extend your search pattern and leave it on autopilot while the data pours down.
Yeah, and data is going to be pouring down. It's all going to be public, and it's going to be made public. So they start taking data in about 2 months from now, after they reach orbit and do some tests, and then the data is pretty much going to be public right away. So
27 days after that, we'll have our first planets?
Pretty much. Well, yeah, maybe 28 days. Some sleepless researcher somewhere will do some quick processing.
To actually need to, no, they've already drafted all the papers. They just need to plug in.
Yeah, they just need to plug in the details. It'll be
Phil to find
Tess-1B.
Yeah.
2.5 months from now.
Oh yeah, of course. They're going to be tests. There'll be test worlds.
There'll be test worlds now.
Yeah, I mean it's funny to think like we still haven't found that Earth 2.0, even though we know of 3,700 confirmed exoplanets, 10 close many more thousand unconfirmed planets, and we still haven't found that Earth-like planet around a sun-like star in the habitable zone, and it's because of that 1 year orbit. That's the Achilles heel for all these missions, is to be able to...
I thought those reaction wheels were the Achilles heel.
Yeah, the reaction wheels are their Achilles heel. That's exactly true.
Yeah, when they dipped Kepler in the river Styx, they held it by the
reaction wheel. Should I just write my article that Tess has lost a reaction wheel now? And
draft all that up.
Yeah.
So that you
keep it in the hopper for at least 3 years, please.
So I'm interested to see what contribution Tess makes to our study of stars. So I think this is one of the really under-cheered aspects of Kepler, is how much it taught us about the variability of stars, about star spots. And presumably Tess will overlap the Kepler field at some point, which will let us establish very cleanly a relationship between Tess measurements and Kepler measurements.
True.
And we can start to answer some of these galactic distribution questions about stars too, in addition to gathering all this planet data.
Well, they've got their guest investigator program. So have you looked through some of the papers and some of the suggestions on the guest investigator program? It's going to be things like that. It's going to be variability of stars, looking at quasars, looking at the interstellar medium. There's a bunch of other work that Tess is going to be able to do, and they've been accepting proposals from all kinds of scientists to use this data for other purposes. So like Gaia, it's going to deliver, other benefits.
Yeah, well, in some ways you can imagine not only is Tess a precursor to James Webb, but it's a precursor to LSST, in the same sense that it's going to be providing this time series data across the entire sky in a different way than LSST will, but it will look for many of the same phenomena with respect to stars that LSST will be sensitive to in a few years.
Exciting.
Yeah. So right now it's on its way to... on its lunar orbit. And it's got such a cool orbit, right? You mentioned this
so
P2
cool.
orbit, but it's going to do a flyby of the moon to get into its final orbit.
Yeah, a little bit of gravity slingshot there. Get it where it needs to go, and then it'll just,
And so when should we expect to see that first data?
You can expect to see it about 2.5 months from now. So it'll take 2 months to get to its orbit, be stable. Once it's in a stable orbit, it won't need to fire engines again. It'll run a few tests, and then it'll take about 2.5 weeks for that first orbit, and then it swings its antenna to Earth, and we download all the data, and then it goes again. So
we've got a couple of questions here.
2.5 months.
Arjun wants to know how many stars are in its visible sphere.
Well, all the stars are invisible. 85% of all the stars in the sky.
Plus a few trillion.
But how many stars will it be observing?
It'll be observing about 200,000 of the brightest nearby stars. That's approximately, because again, it can only stare at a single swath of the sky for about 27 days, and so it can only really capture the few thousand brightest in that patch, just because it doesn't have enough of the integration time on its CCDs to get more. So about
its
200,000 total.
observing depth will change from patch to patch depending on that particular demographic of stars in that patch.
Yeah.
Nancy Graziano wants to know what band is it going to be looking in?
It's going to be looking in a broadband, just like Kepler. So visible-ish, but pretty broad.
I want all the light.
All the light.
All the light you can, yeah.
Yeah, it's also radio. No, it's not radio telescope.
I mean, it has an antenna to go to Earth, but that's about it.
Man.
Thanks.
You could turn it into a detector.
So I don't know. So how does this make you feel? Do you feel more now or less nervous about James Webb?
I have the same feelings about James Webb. This has nothing to do with James Webb. This is all about Tess and planets.
Just Tess. Can't Tess live on its own merits?
Yeah, it is its own.
Can't we love all of our spacecraft missions equally?
Is this the first major scientific spacecraft launched by SpaceX?
I don't know.
That's a good question.
Yeah, I can't think it is.
No, they did. Didn't they launch a NOAA satellite recently?
Mm-hmm.
Okay, fair enough.
I swear they launched it was GOES or something like that recently.
Really? I thought GOES-R, or was it GOES-S was the most recent one?
I think S is the most recent.
Anyway, I think they launched a NOAA satellite not too long ago, but it's certainly one of the first.
They're not going to be launching InSight. That's on an Atlas, which is coming up in a couple of months.
Yeah.
Man.
Weeks now.
Yeah, I guess so.
Yeah, InSight's
3 weeks.
pretty soon.
Yeah, it's going to be a quick bunch of launches. And the other thing is that SpaceX is going to be using its Block 5 configuration probably later on this month, which is going to be sort of its next new streamlined version of the booster, which is why they haven't been recovering as many of these boosters as they have recently. All right, well, let's move on. Although I don't feel like I want to. I feel like we could just talk about Tess all day.
Bask in test.
Yeah.
Tess.
It launched.
I so look forward to the first test planet.
Now, of course, we don't know.
Then,
We've been in this
the
show.
1000th.
So somebody please tell us if something horrible has happened to Tess since we started.
No.
I'm saying just tell us. Just let us know.
I will say.
Just let us have this moment.
Just have this moment.
I checked on it before we started recording, and stage 1 was fine, and stage 2 is fine, and the telescope detached from stage 2, and it was all fine.
Kimberly's like a nervous mom here.
I feel.
Make sure you put the stocking cap on.
Make sure you.
Did you finish firing your stage 2 rocket engine? Okay, good.
Did anybody see how small Tess was in the rocket fairing?
It's so tiny.
It was so tiny. It was like this little tiny spacecraft and this huge standard SpaceX fairing, the kind of thing you could hide a bus inside. And so it's this little block of spacecraft down at the very bottom of the.
Was Tess the only part of the launch?
That's the only thing they launched, yeah. And so the rest of it was just open space.
Giant fairing.
Yeah, in this huge fairing. But it had a pretty complicated, to do out to this lunar orbit, it needed a lot of delta V to get out there. So it did need all of that rocket. But still, it's hilarious to see what it looks like in that configured. Larry Beckham says both solar arrays were deployed and operational. So Tess is fine so far.
Yay.
All right, Paul, Matt, Sutter, let's talk about a lost planet.
Yeah, so this is an interesting article, and I don't know basically anything about it. It's studying a certain kind of meteorite. I can't even pronounce the kind of meteorite.
Urolite.
Is it a ureolite?
Ureolite.
Ureolite?
Yeah.
I don't know.
Yeah.
And I was hoping to appoint Morgan as my deputy Kraken on this result.
I should have read it before we started.
Well, now you gotta get Kraken. Now on this, so what these researchers did, there's this very, very, very special, very rare kind of meteorite called
ureolite.
Ureolite. And inside ureolite, there are tiny diamonds. They're just like nanometer, micrometer scale diamonds. And those diamonds could have only been formed under high pressure. And so the thinking was that whatever the parent body was of these meteorites, like some asteroid, suffered some massive collision in the early days of the solar system when massive collisions happened all the time, fragmented. In the shock waves, there is intense heat and pressure for very brief moments of time, fused the graphite and squeezed it down to make little bits of diamond. And then the meteorites float around the solar system for billions of years, fall from the sky, kill some dinosaurs, hit a car, whatever. And then you can see these little diamonds. And you know that this piece of rock had to suffer some massive collision. Well, some very recent analysis noticed that some of these diamonds that were embedded in the ureolite had other elements included in the diamond body itself, like chromite, phosphate, and iron nickel sulfides. And they propose that the only way to get those extra elements shoved inside the diamonds isn't from a single brief catastrophic event, but by having this piece of rock experience incredibly high temperatures and pressures over long time scales, which means it once had to be inside of something the size of a moon or a Mars. And then that had to suffer some catastrophic event and fragment and turn into meteorites that fall to Earth.
Where's your need for a skeptical point of view on this?
Like, is that a legit?
That is legitimate. I will say
that
is legitimate. The same sort of thing happens here on Earth with diamonds that are formed in our mantle or deeper, is that the carbon's under intense pressure for a long period of time. And while it is forming, it traps these micron-sized inclusions of whatever other material was around at the time, and just get stuck there, and then eventually they come up to the surface and we see them. That's a thing that happens here on Earth as well, so that seems legit to me.
Yeah, this story basically checks out in my mind. I mean, let's think about some of the things we have already seen for meteorites. We have iron meteorites that likely were the cores of planetesimals or protoplanets that had differentiated before being broken apart. So we know that there were impacts violent enough to break apart these large objects and sort of spring free their core. We have meteorites that show shock damage to them, indicative of being struck in these sorts of high velocity collisions. We have the moon, which we're pretty sure was created when a Mars-sized object hit an Earth-sized object, namely the Earth. And unless we are super, super lucky, it's plausible to imagine that Mars-sized objects hitting Earth-sized objects early in the solar system wasn't a particularly uncommon thing. And so all of the sort of pieces here, and the creation of diamonds in the center of these differentiated bodies isn't an uncommon thing, as we know from the Earth, that you have those incredible heats and pressures necessary to do that. So all of the elements here sort of add up. And I think probably in general, we underestimate the violent lives that planetesimals led early in the solar system. We often think of, big rock forms, smash, break apart, falls as a meteorite on Earth millions or billions of years later. In reality, these things probably were smacked over and over again, incorporated into rubble piles of other objects, and broken up again. And to have this long, complicated life early on in the solar system doesn't strike me as a particularly outlandish idea.
It's a really fascinating idea that you can sort of trace back. I mean, although the history of the early solar system is long gone, that you can have these tiny little clues that, you know, because they found a diamond of this consistency, that meant that there had to be a planet of X mass and size to produce this kind of debris. It's an absolutely fascinating result, and you can just sort of imagine, as more of this is discovered, as they explore more of the Earth to find more of these little remnants, maybe they'll be able to put together and sort of find, oh, we found a second diamond that came from that same planetoid that was long gone.
Yeah, that was going to be my next question, is how far can we push this? I understand the meteorites are an excellent window into the early solar system. How far can one sample like this tell us about the state of the good old days?
It can actually tell us a lot, I would say, depending on what those little inclusions within the diamonds actually contain. So something that we're starting to understand on Earth is that some of our deep mantle diamonds actually encapsulate material that can only be formed in the presence of water, for example. So that's something that we're starting to learn about diamonds forged within our own planet, is that they can contain evidence of whatever fluids might have been around when that diamond formed. Diamonds essentially are like a tiny little time capsule that, unless you break apart the diamond in just such a way, it's going to preserve whatever it is inside of it.
It's like how you can make dinosaurs out of amber.
Amber?
Right?
Yeah.
You could just carve open these diamonds, extract the alien DNA, and make aliens from it.
Yeah.
This whole meteorite as time capsule idea is the sort of basic idea behind the Lucy mission, which we haven't talked about that much. But Lucy, launching in the early 2020s, is going to take this long, winding path through Jupiter's Trojan asteroids. And although it won't pick up individual rocks and it won't study them at the microscopic scale, the idea is that if Jupiter migrated early on in the history of the solar system, it would have brought with it the Trojan asteroids. And so wherever Jupiter went, whatever Jupiter experienced might be recorded in the Trojan asteroids in a way that we can try to go back and read to unpack what might have happened to one particular body early in the solar system.
Extremely cool. Morgan, tell us about how Russia's getting out of the rocket game, the international launch game.
Yeah, this is I don't really know how to describe this. It's like the most surprising, least surprising piece of news. So go back 5 years to 2013, and Russia has about 50% of the commercial space launch market, which is about $5.5 billion a year. 5 years later, SpaceX has 50% of the commercial launch market, and Russia has 10% of the market and falling. And so the head of the Russian space program, who's one of the deputy prime ministers of Russia, basically said this week that they're done trying to compete with commercial companies to launch commercial satellites. And instead, they're going to refocus their efforts not in launching rockets, but in building the satellites themselves, which is a more lucrative business. It's more like a $15 billion a year business, and one that isn't so quickly being encroached upon by companies like Blue Origin or SpaceX.
Is this the canary in the coal mine?
I think so. I mean, think about it. Russia, or the Soviet Union, was literally the original rocket nation. They were the original space launch power. And they really never responded to the emergence of lower cost, potentially reusable rockets. And they've seen their market share totally decimated.
Yeah.
And I think this is what we're going to see happen to any company or any nation that doesn't respond to these new developments is they'll continue to have their own rockets to launch their own governmental and national security payloads, but it's going to become a harder and harder market to get any foothold in if you don't have bottom of the barrel prices. It's basically the Amazonification of the rocket business. If you're a brick and mortar rocket company, then you better have a really solid plan for how you're going to become the next Amazon, or you're just going to get Bezos'd by Blue Origin.
How do you compete against SpaceX, especially when they get the BFR going? For whatever 10% the launch cost to launch an enormous payload into space from
you've got to build a cheaper rocket.
You have to build a cheaper rocket or you go out of business. And now, I think we mentioned this last week, SpaceX is now doing these launches every 2 weeks. Right? Like this was the 24th successful landing of a SpaceX landing stage, first stage. Like, boring.
Right. Yeah, I mean, think about it. 10
rockets landing on drone.
10 years ago, SpaceX was launching their first rocket. 10 years ago. Today, they have 50% of the market. That's the sort of market disruption that we basically have traditionally only seen by technology companies. That much changed that rapidly. And it's easy to imagine that 2 years from now, it's going to be 70%. And in a sense, almost, SpaceX is going to become the Microsoft of the launch world, and we're going to start wanting competition again, because it's going to push out all these other companies. And no company, no matter how successful early on, sort of will continue to innovate at that pace if they're not pushed by another company. And so we want Blue Origin to keep up with them. We should want the United Launch Alliance or Russia or China or India to develop competitive rockets to ensure that we keep moving at this pace. After 60 years of nothing happening, basically, we suddenly have competition and innovation.
Yeah.
Let's try to hang on to that and not just enter a duopoly again 5 years from now.
And you're exactly right? SpaceX running away with this market would be a disaster. We're all excited about SpaceX because they are getting this early. They are flattening the playing field. They are producing a tremendous amount of innovation. And the thing that really excites me is the fact that you've got Blue Origin nipping at their heels to, the richest man in the world is investing in this rocket company and has demonstrated reasonable rocket technology, not to orbit yet, but all the pieces are coming together. They're not far behind. United Launch Alliance, which I know a lot of people feel is the incumbent, is the dinosaur, to use that analogy. They've got their plans for the Vulcan rocket, which is a fairly smart way to approach, make the engines themselves reusable. Speaking of which, we should have someone from ULA come on the show sometime. I'd love to have them explain the Vulcan, because it's a pretty exciting idea. So, and then you've got all of this great competition down on the small sat side. You've got Rocket Lab, you've got these balloon satellites, you've got a lot of really interesting small sat providers as well. And so I think we should all be really excited about what's happening with SpaceX, but we should also be a little nervous that we're now getting kind of what we hoped for, which is SpaceX just destroying the entire marketplace and turning it into a monopoly, which would not be good at all.
They're still in my good graces right now. They just launched tests.
Yeah, no, absolutely.
Kimberly, it's a very one-track mind right now.
Test. Did you launch tests? Are you about to launch tests? Tests. Yeah, you're in a good books or bad books, depending on your status with tests.
Can you blame me?
No.
What do you got, Fraser?
I'm going to talk. Okay, so I made a terrible error in judgment. I forgot that this is a podcast. So what I wanted to do is I wanted to show these amazing images from the European Southern Observatory of a bunch of planetary disks. So I'm going to bring up this picture, and we're all going to. I don't know if the other folks can get this on your computers. We can ooh and ah that for a second, but I will throw a curveball and talk about SpaceX for one more second as well. So I'm just going to bring up this picture. Check this out. Have you guys able to sort of see these images? Yes. ESO released a collection of planet-forming disks, and they're all just these really stunning images of different orientations of disk material, and you can just see these young stars with these planets forming around them, and it just sort of shows you the capability. And this is done using a new instrument from the European Southern Observatory's very large telescope called the Sphere instrument, and its job is to find objects, cooler infrared objects like this. And
I love the one on the bottom left that is these really thin almost rings of material.
Yeah, and there's another one that looks a bit like a yo-yo. So, and I
like the yo-yo one.
Yeah, and I want to apologize in advance to all the people who are listening on the podcast. So I'm going to do you one other favor here. Let's see. I'm going to tell you about a super weird tweet that Elon Musk posted to Twitter like a couple of days ago, and we jumped all over it. So Elon Musk just a couple of days ago said, "This is going to sound crazy, but SpaceX will try to bring an upper stage back from orbital velocity using a giant party balloon." And
something about a bounce house too.
Yeah, and then later on he said that they're going to land it on a bouncy castle. But we sort of dug into, and there was a really interesting conversation that happened in that tweet after that, and we kind of dug into what was going on, what was he talking about, and the gist is. And this is sort of an idea that's gone around quite a bit, is using some kind of inflatable parachute / balloon that provides more drag on a piece of space junk, or in this case an upper stage of the rocket, that will allow it to be able to re-enter the Earth's atmosphere. And so there's sort of two directions this goes. One is that other sort of space scientists have looked into this as a way to, if you've got a spacecraft that's going at a really high velocity, it's going to tear itself apart, that you can deploy some kind of balloon that will slow it down so it won't actually burn up in the Earth's atmosphere. But the other one is this really great idea about space junk. So you will fly pretty much every piece of potential space junk with some kind of inflatable balloon that's attached to it. And then when your upper stage booster has finished its job, it will inflate this gigantic balloon and then continue to remain space junk. And what this will do is dramatically increase the cross section of the piece of space junk so that it re-enters the Earth's atmosphere much more quickly. It would take a matter of, say, weeks or months instead of years. And one of the potential requirements down the road is that that anyone who is going to be launching spacecraft in the future have to consider how they're going to bring that spacecraft back to Earth. What is their method to minimize the amount of space junk that they're adding? And when you consider the fact that SpaceX is going to be launching 4,000, eventually 12,000 satellites in a sort of relatively low Earth orbit to provide this Starlink internet system, they're going to have to think about how much junk they're putting out in space. And so you can see them starting to test out different techniques. So we're going to keep tracking the story, but I thought it was really interesting to sort of see. We didn't get any official response from SpaceX yet, but we'll go from there. Yeah, someone in the chat is mentioning. I apologize. I'm like half in sunlight right now. Apparently, there's some kind of burning orb in the sky here on Vancouver Island. I'm completely
You've
unfamiliar
discovered the day
with.
star.
Yeah, I'm completely unfamiliar with this thing.
It's
but
weird.
Yeah, no, we've got our we're doing renovations, and my window's sort of torn apart. So we'll get some kind of shade back next week. Anyway, so let's wrap things up. And now it's time for our guest, which I will remember to say in order at some point in the future. That was a great guest. Thanks, Kevin. All right, let's move on to our shameless self-promotion. Paul, tell me something super interesting that you're working on or just did.
We have a brand new Astro Tour that just launched. It's super cool. We're going to Costa Rica tropical jungles. Now you might think, wow, tropical jungles sound great. What does that have to do with astronomy? Turns out Costa Rica, because of all their efforts in ecotourism, have some amazingly dark skies. Seriously, you can use Dark Sky Finder. And I remember you and I were like hunting, like where could we go for stargazing sessions during this trip. Turns out we just like walk outside.
Yeah.
From our hotel, from our resort.
Yeah, well, the backyard of pretty much every single part of the wherever we're going to be is incredibly dark skies, and so we're going to get our hands on some really great equipment. We'll set it up. We'll do some sky watching every night. We'll see volcanoes. We're going to see the wildlife. I've been to Costa Rica before. My wife's been a couple of times now. It is one of my favorite places on earth, and I can't wait to share it with
we're going to Guanacaste. We're going to Arenal. We're going to Monteverde. We're going to San Jose. It's a really, really cool tour. Flights are included in the price, all inclusive, the whole deal. Go to astrotours.co and sign up now. This is gonna be a hot one. It's gonna be a hot one. And so get on that. It's just $500 to lock your place in.
Kimberly.
All right, so this past weekend, I spent Saturday and Sunday covering the March for Science, which there's a large event here in DC, and of course events all over the world. So I was covering that event. And then, of course, the TESS launch. Obviously, I spent my time getting ready for the TESS. Okay, so TESS. Let me tell you all about
it. You started again.
Or
we
you
went
could
around
just
the horn.
listen to the podcast of Weekly Space Hangout, where I go on a 20-minute rant about TESS, because it's awesome. Anyway, that's what I've been doing, and I've been perfectly happy with TESS.
Morgan.
Yeah, yesterday over at SciShow Space, my longest ever video, 7 minutes, came out. I know I work real hard. All about moon buggies, which it turns out are freaking amazing. And so if you ever wondered what would it take to design a car for like $100 million a model, the moon buggy is the answer. And it turns out you get all the bells and whistles.
I'm so glad you are providing scripts to SciShow Space. They've been really great episodes.
It's so much fun.
I've been really enjoying them. Good work. Although it's very strange. I can always tell when it's your scripts, but I see your words come out of other people's mouths. So, you should get
It's a weird feeling for me. I've never really get over the fact that it's like, hey, I wrote those things, and yet that doesn't sound like me.
Fraser, what you been up to?
Well, so I did a live QA on Monday on my YouTube channel, and I think I'm going to bring that back for a little while. In fact, I've got joining me next Monday on my channel is going to be Isaac Arthur, futurist and regular collaborator with many of us and people, but I don't think people have really had a chance to talk with him live. So we're just going to hang out and answer people's questions. So if you want to check that out, come over to my YouTube channel. And then I also mentioned earlier this week that I'm bringing back the virtual star party. So
That's a blast from the past.
It is total blast from the past. This is something that we did many years ago, and we had to shut it down because it was just cat herding every single week because there were so many different astronomers. They had different skies, different technology problems, and it just got to a point where we just couldn't provide a regular, stable existence. So, but now we've got a partnership with Oceanside Photo and Telescope, and they are setting up a permanent automated telescope in a wonderful dark sky location down in California. So we will have a telescope, like a baseline telescope they will always be able to use. So I think that gives me the confidence. And not only that, they're building a space telescope that we might be able to use as well. So
whoa.
Yeah. So
just casually tossing that out there.
Yeah.
It might be a space telescope.
Yeah. So hopefully with that and other people, we're going to be able to sort of bring back the star parties. And my hope is to bring all of the co-hosts here to come hang out and nerd out about space and astronomy live as we look at pictures of the night sky. So stay tuned. Probably in the next couple of weeks, we'll be bringing that back. And now that I've said it publicly, I'm now duty bound to make it happen.
It has to happen.
Yeah.
Yeah.
All right. let's wrap things up. Thanks everyone for joining us this week. Go, as always, to the wshcrew.space to join the wonderful community that joins us every week. And we'll see you all next week. Goodbye.